Here's what's wild. The pretty pictures from the James Webb Space Telescope? They're not just pretty. The data reveals a universe that's way bigger and older than we ever thought. The implications extend to everything. Consider this. Our current models of galaxy formation? Utterly completely wrong. We thought we understood the age of the universe. The evidence shows we were off by billions of years. And that's the good news. What if the entire framework we use to understand the cosmos is fundamentally flawed? The analysis continues, and the deeper we looked, the scarier it got. 600 galaxies, all breaking the rules. We're talking about galaxies that are far too massive, far too early in the universe's timeline. It's like finding fully grown adults in a kindergarten classroom. They simply shouldn't be there. The standard cosmological model, the one we've been using for decades, struggles to explain this. It predicts a gradual buildup of galaxies over billions of years, starting with small clumps of stars and gas that slowly merge and grow. But the James Webb Telescope is showing us that some galaxies were already huge just a few 100 million years after the Big Bang. That's not supposed to happen. These early galaxies aren't just a little bit bigger than expected. They're massive. Some are comparable in size to the Milky Way, or even larger. Imagine trying to assemble a skyscraper in a week. That's the kind of timescale problem we're facing. How did these galaxies form so quickly? What processes allowed them to accumulate so much mass in such a short amount of time? These are the questions that scientists are now scrambling to answer. And the answers, when they come, could fundamentally rewrite our understanding of the early universe. Consider the implications. If our models of galaxy formation are wrong, what else are we wrong about? Are our estimates of the age of the universe off? Are we missing some crucial ingredient in the cosmic recipe? It's not just about tweaking the existing models, it's about potentially throwing them out altogether and starting from scratch. That's a daunting prospect, but it's also incredibly exciting. It means that we're on the verge of a major breakthrough in our understanding of the cosmos. Scientists discovered that the light from these early galaxies is also different from what they expected. It's richer in heavy elements like oxygen and carbon than it should be. Where did these elements come from? They're forged in the hearts of stars, and it takes multiple generations of stars to produce the amounts we're seeing in these early galaxies. This suggests that star formation in the early universe was far more efficient and rapid than we thought. It also raises questions about the types of stars that were forming. Were they different from the stars we see today? Were they more massive, shorter-lived, and more prolific at producing heavy elements? The data reveals an intense burst of star formation in these early galaxies, a period of rapid growth and development that defies our current understanding. It's like the universe was in a hurry to create these massive structures, and we don't know why. And then there's the issue of dark matter. Dark matter is an invisible substance that makes up the majority of the mass in the universe. It's thought to play a crucial role in galaxy formation, providing the gravitational scaffolding that allows galaxies to form and grow. But the James Webb Telescope's observations are challenging our understanding of dark matter as well. The distribution of dark matter in these early galaxies doesn't seem to match our models. It's either more concentrated or more diffuse than we expect, depending on the galaxy. This could mean that our understanding of dark matter itself is incomplete. Perhaps dark matter particles interact with each other in ways we don't yet understand. Or perhaps there are other forces at play that we're not taking into account. This means that the James Webb Telescope isn't just challenging our understanding of galaxy formation. It's challenging our understanding of the fundamental building blocks of the universe. It's forcing us to reconsider everything we thought we knew about the cosmos. The implications extend to our understanding of the Big Bang itself. If galaxies formed much earlier and faster than we thought, does that mean the early universe was different from what we imagined? Was the expansion rate of the universe different? Were the initial conditions different? These are all questions that scientists are now grappling with. And the answers, when they come, could have profound implications for our understanding of the origins of the universe. This is more than just a scientific puzzle. It's a philosophical challenge. It's a reminder that our understanding of the universe is always evolving, and that there are always new mysteries to be uncovered. It's a humbling experience to realize how much we still don't know. The analysis continued. The more we learn, the more we realize how much more there is to learn. And that's what makes science so exciting. It's a never-ending quest to understand the universe and our place in it. And the James Webb Space Telescope is giving us a front-row seat to this incredible journey. So, what's the solution? How do we reconcile these new observations with our existing models? That's the million-dollar question. And the answer, when it comes, will likely involve a combination of new ideas and new observations. It's going to take a concerted effort from scientists around the world to unravel this mystery. The James Webb Telescope is providing us with the data we need to solve this puzzle, but it's up to us to interpret that data and to develop new theories that can explain what we're seeing. It's a daunting task, but it's also an incredibly exciting one. And then there's the black hole problem. How could black holes possibly form so quickly? We're talking about supermassive black holes, billions of times the mass of our sun, appearing when the universe was just a few 100 million years old. That's like finding a fully grown oak tree sprouting from the ground the day after you plant an acorn. It just doesn't compute. Our current understanding of black hole formation relies on the idea of stellar mass black holes, the remnants of massive stars that collapse at the end of their lives. These stellar mass black holes can then merge and accrete matter, gradually growing over billions of years into the supermassive behemoths we see at the centers of galaxies today. But the early universe doesn't seem to allow for that slow, steady growth. There simply wasn't enough time. Scientists discovered a few potential solutions have been proposed. One idea is the concept of direct collapse black holes. This theory suggests that under certain extreme conditions, vast clouds of gas could have collapsed directly into massive black holes, bypassing the need for stellar intermediaries. The conditions required for direct collapse are incredibly specific: pristine gas clouds, free from heavy elements, and exposed to intense radiation. Finding evidence of these conditions in the early universe is proving challenging. Another possibility involves much higher accretion rates than previously thought. Maybe these early black holes were simply much more efficient at gobbling up surrounding matter, growing at an accelerated pace. However, even with maximal accretion rates, it's difficult to explain the sheer size of these early supermassive black holes. The numbers just don't quite add up. And then there's the seed black hole problem. Even if you can get a direct collapse black hole or a rapidly accreting black hole, you still need a seed to start the process. Where did these initial seed black holes come from? Were they the result of exotic physics we don't yet understand? Did they form in regions of extreme density fluctuations in the early universe? These are open questions that continue to fuel intense debate within the astrophysics community. What's particularly troubling is that the James Webb Telescope is finding these supermassive black holes in galaxies that are surprisingly small and well-ordered. We would expect to see them in the chaotic merging systems that were thought to be prevalent in the early universe. The presence of these black holes in relatively quiescent galaxies suggests that something fundamentally different was happening in the early universe. Consider this: if these black holes formed through mergers and accretion, they should have disrupted the galaxies they inhabit. We should see evidence of tidal forces, distorted structures, and enhanced star formation. But the galaxies observed by Webb appear remarkably undisturbed. This suggests that the black holes may have formed before the galaxies, perhaps even playing a role in their formation. This is a radical idea, but it's one that's gaining traction among some scientists. The thought is that these early black holes could have acted as seeds around which galaxies eventually formed. Their immense gravity could have attracted and compressed surrounding gas, triggering star formation and shaping the structure of the galaxies we see today. This would flip our current understanding of galaxy formation on its head. Instead of black holes forming within galaxies, galaxies would be forming around black holes. It's a mind-bending concept, but it's one that's consistent with the latest observations from the James Webb Telescope. Further examination revealed this challenges our understanding of the relationship between black holes and their host galaxies. We've always assumed that galaxies came first and that black holes formed later as a result of galactic evolution. But these new observations suggest that the opposite may be true, at least in the early universe. Scientists discovered that this has profound implications for our understanding of the co-evolution of black holes and galaxies. If black holes are indeed playing a role in shaping the galaxies that surround them, then we need to rethink our models of how these two fundamental components of the universe interact. Measurements showed if we're wrong about black hole formation, are we also wrong about the galaxies they live in? Are the galaxies older than we think? The analysis continued, and the more we learn, the more these early galaxies resemble scaled-down versions of what we see today. This kept me up last night. Honestly, I couldn't stop thinking about it. We're talking about missing middle children, black holes that should be there, according to our current models, but aren't. Let's examine this a bit closer. We have supermassive black holes at the centers of most galaxies, including our own Milky Way. And we have stellar mass black holes, the remnants of collapsed stars. But what about the black holes in between? The ones with masses hundreds or thousands of times that of our Sun. These intermediate mass black holes, or IMBHS, are the theoretical missing link between the small and large ones. They should be relatively common, especially in dwarf galaxies and the outer reaches of larger galaxies. They're predicted to be the seeds that eventually grow into supermassive black holes. So where are they? Well, we've found a few candidates, but it's been a struggle. They're elusive, hard to detect, and often hidden within dense star clusters. Until recently, we just didn't have the tools to find them definitively, especially in the early universe. And that's where the James Webb Telescope comes in. With its unprecedented sensitivity and resolution, Webb is peering back in time, observing galaxies as they were billions of years ago. And what it's not finding is almost as important as what it is finding. Measurements showed the early universe, teeming with supermassive black holes, far more than our models predicted. But where are the IMBHs that should have been their precursors? If these supermassive black holes grew from smaller seeds, where are those seeds hiding? The implications extend far beyond just a missing population of black holes. If our understanding of black hole formation is flawed, it calls into question our entire model of galaxy evolution. Are we missing some fundamental process that governs the growth of these cosmic behemoths? Scientists discovered the problem is not just that we're not seeing them, it's that their absence creates a cascade of problems for our understanding of how galaxies and black holes co-evolve. Consider this. Our models of galaxy formation rely on a hierarchical process, where small structures merge to form larger ones. Dwarf galaxies, with their relatively simple structures, are thought to be the building blocks of larger galaxies, and these dwarf galaxies should host intermediate mass black holes at their centers. But the observations from Webb are painting a different picture. The early galaxies appear to have formed rapidly, with fully formed supermassive black holes already in place. There doesn't seem to be enough time for these black holes to have grown from smaller seeds through the standard accretion process. The analysis continued. If these supermassive black holes appeared so early and grew so quickly, it suggests that they may have formed through a different mechanism altogether. Perhaps they formed directly from the collapse of massive gas clouds, bypassing the intermediate mass stage entirely. Here's what's wild. If that's the case, then our entire understanding of the black hole population needs to be revised. We may have overestimated the number of IMBHs that should exist, and we may need to rethink the role they play in galaxy formation. This means we might be wrong about the fundamental building blocks of galaxies. If the early galaxies formed differently than we thought, it calls into question our models of how the universe evolved from its earliest moments. Further examination revealed this isn't just a theoretical exercise, it has real-world implications for our understanding of the universe around us. For example, the search for gravitational waves relies on accurate models of black hole mergers. If we don't know the true population of black holes, we may be missing important signals. And then there's the question of dark matter. Some theories propose that dark matter is made up of primordial black holes, formed in the very early universe. If the population of IMBHs is different than we thought, it could affect our understanding of the nature of dark matter. The evidence shows we're not just talking about a few missing black holes. We're talking about a potential paradigm shift in our understanding of the universe. It's a challenge to our current models, but it's also an opportunity to learn something new and profound about the cosmos. Meanwhile, astronomers are scrambling to revise their simulations, incorporating the latest data from Webb. They're exploring alternative scenarios for black hole formation and galaxy evolution, and they're searching for new ways to detect these elusive intermediate mass black holes, hoping to finally solve the mystery of the missing middle children. This means that the next few years are going to be an exciting time for cosmology. As Webb continues to collect data, we can expect even more surprises and challenges to our current understanding. It's a reminder that the universe is far more complex and mysterious than we ever imagined. Scientists discovered that the absence of these intermediate mass black holes is forcing them to reevaluate their assumptions and explore new possibilities. It's a testament to the power of observation and the importance of questioning our existing models, and honestly, that's what makes science so exciting. It's a constant process of discovery where we're always learning and refining our understanding of the world around us, even when it means admitting that we were wrong. December 2023, an astrophysics conference in Chile. The room was buzzing about new Webb data, the kind that makes careers. But one presentation seemed to drain the color from the room. It wasn't the discovery of a new galaxy or even a black hole. It was the absence of something, a very specific absence related to dark matter. See, our models of galaxy formation rely heavily on dark matter halos. These halos are like scaffolding, providing the gravitational framework for galaxies to assemble. The idea is that smaller clumps of dark matter merge over time, eventually forming the massive halos that host galaxies like our own Milky Way. Within those halos, we expect to find a hierarchy of dark matter structures, from the largest to the very smallest. And it's in these smallest structures where the trouble begins. The standard cosmological model predicts that there should be countless numbers of small, dense clumps of dark matter orbiting within larger galaxies. These clumps, often referred to as subhalos, are thought to play a crucial role in shaping the distribution of stars and gas within galaxies. They act like gravitational stirrers, influencing the way galaxies rotate and how stars are formed. But here's the rub. Webb is not seeing the predicted number of these small dark matter subhalos. It's like expecting to find a bustling city teeming with life, only to discover a ghost town. The galaxies Webb is observing, especially those in the early universe, appear to be far smoother and more uniform than our models predict. The evidence shows that the small-scale structure of dark matter is simply not there, or at least not in the abundance that we expect. Why is this a problem? Because it challenges the very foundation of our understanding of how galaxies form and evolve. If dark matter isn't behaving the way we think it should, then our entire cosmological framework may need a serious overhaul. The implications extend beyond just galaxy formation. Dark matter is thought to make up about 85% of the matter in the universe. It influences everything from the expansion rate of the universe to the distribution of galaxies on the largest scales. If we don't understand the nature of dark matter, then we're missing a huge piece of the cosmic puzzle. Consider this. If the small-scale structure of dark matter is suppressed, it could mean that dark matter particles are interacting with each other in ways we don't yet understand. Some theories propose that dark matter particles can collide and scatter, smoothing out the distribution of dark matter on small scales. This could explain why we're not seeing the predicted number of subhalos. Alternatively, it could mean that our understanding of the early universe is incomplete. The initial conditions of the universe, the seeds from which all structure grew, may have been different than we thought. Perhaps there were fewer small-scale fluctuations in the early universe, leading to a smoother distribution of dark matter today. And then there's the possibility that dark matter isn't even made up of particles at all. Some alternative theories propose that dark matter is a modification of gravity rather than a new form of matter. These theories, known as modified Newtonian dynamics, MOND, attempt to explain the observed behavior of galaxies without invoking dark matter at all. While MOND has its own challenges and doesn't fully explain all the cosmological observations, the absence of small-scale dark matter structure is certainly giving these alternative theories a new look. It's like the universe is whispering, maybe you should consider other possibilities. Measurements showed this isn't just about tweaking a few parameters in our simulations. This is about questioning some of the most fundamental assumptions we have about the nature of dark matter and the formation of cosmic structure. It's about being willing to entertain the possibility that we might be fundamentally wrong. Scientists discovered the universe may not be structured exactly as we thought, and dark matter may not be exactly what we thought. Here's what's wild. We now need to consider that dark matter interacts with itself. It changes our understanding of the early universe and opens the door for the craziest theory of all. That dark matter doesn't exist. The analysis continued. The shifting sands of dark matter are forcing a re-evaluation of everything we thought we knew. Everyone expected a neat, hierarchical universe. Galaxies nestled within halos of dark matter, like ornaments on a cosmic Christmas tree. The simulations predicted it. The math seemed to support it. But the universe, as Webb is showing us, apparently didn't get the memo. The models, painstakingly constructed over decades, started to look wrong. Not just slightly off, but fundamentally flawed. Imagine building a bridge based on flawless blueprints only to discover the laws of physics themselves have shifted. That's the scale of the problem here. The simulations, which accurately predicted the large-scale structure of the universe, the cosmic web of galaxies and voids, completely failed to reproduce what Webb was seeing at smaller scales. The number of small galaxies, their star formation rates, their chemical composition, everything was off. Way off. It's like trying to fit a square peg into a round hole, except the peg is the entire standard model of cosmology, and the hole is the actual universe. Think about the implications. These simulations aren't just pretty pictures. They're based on our best understanding of gravity, dark matter, and the expansion of the universe. They're the foundation upon which we build our understanding of cosmic history. And now that foundation is cracking. What went wrong? Well, that's the trillion-dollar question. One possibility, as we touched on, is that our understanding of dark matter is incomplete. Maybe dark matter particles interact with each other in ways we haven't accounted for. Maybe they're lighter than we thought, or maybe they have some other exotic property that's throwing off the simulations. Consider the possibility that dark matter isn't a single type of particle, but a whole zoo of different particles, each with its own unique properties. This dark sector could be just as complex and diverse as the visible universe, with its own forces and interactions. If that's the case, then our current simulations, which assume a simple, vanilla version of dark matter, are simply too simplistic to capture the full picture. Another possibility is that our understanding of galaxy formation is incomplete. Maybe there are processes at play that we haven't even considered, some feedback mechanism that regulates star formation in small galaxies and prevents them from growing too quickly. Perhaps the energetic outflows from supermassive black holes, even in dwarf galaxies, play a much more significant role than we previously thought. Or maybe there are subtle effects related to the rionization of the universe, the period when the first stars and galaxies ionize the intergalactic medium, that are altering the properties of small galaxies. The problem extends beyond just the number of small galaxies. Webb is also revealing that these galaxies are far more mature and evolved than our simulations predict. They have older stellar populations, higher metallicities, and more complex morphologies than they should, given their size and age. This suggests that galaxy formation is a much more rapid and efficient process than we previously thought. Small galaxies are somehow able to form stars and enrich themselves with heavy elements much faster than our simulations allow. It's like finding a toddler who's already writing novels and composing symphonies. It defies everything we thought we knew about child development, and it forces us to rethink the underlying mechanisms that govern human learning. The failures of these simulations aren't just an academic problem. They have profound implications for our understanding of the universe. If we can't accurately simulate the formation of galaxies, then we can't accurately predict their evolution. And if we can't accurately predict their evolution, then we can't accurately infer the properties of the universe from the galaxies we observe. This is particularly problematic when it comes to dark matter. As we've discussed, dark matter is invisible, so we can only infer its presence and properties by observing its gravitational effects on visible matter. But if our simulations of galaxy formation are wrong, then our inferences about dark matter may also be wrong. We might be overestimating the amount of dark matter in galaxies, or we might be misinterpreting its distribution. Or, even more radically, we might be completely wrong about the nature of dark matter itself. Consider the possibility that what we call dark matter isn't actually a new form of matter at all, but a modification of gravity. As we mentioned before, modified Newtonian dynamics, MOND, proposes that gravity behaves differently at very low accelerations, such as those found in the outer regions of galaxies. MOND can explain some of the observed behavior of galaxies without invoking dark matter, but it has its own challenges and doesn't fully explain all the cosmological observations. However, the failures of the standard simulations are giving MOND and other alternative theories a new lease on life. The problem is so fundamental, so pervasive, that it's forcing scientists to reconsider some of the most basic assumptions about the universe. Are we missing something crucial in our understanding of gravity? Is our picture of the early universe fundamentally flawed, or is there something else entirely that we haven't even considered? These are not easy questions to answer, and they may require a complete overhaul of our current cosmological models. But one thing is clear: the James Webb Space Telescope is not just confirming our existing theories, it's challenging them. It's pushing us to the limits of our knowledge and forcing us to confront the unknown. The implications extend far beyond the realm of astrophysics. If our understanding of the universe is fundamentally wrong, then what else are we wrong about? What other assumptions are we making that are holding us back from making progress in other fields of science and technology? The universe, as revealed by Webb, is a humbling and terrifying place. It's a place where our best theories can crumble in the face of new evidence, where the unknown vastly outweighs the known, and where the only constant is change. This leaves everyone wondering, is it time to burn the whole thing down and start over? There's a growing tension within the scientific community. It revolves around something called lambda CDM, which is our standard model of cosmology. Think of it as the blueprint we use to understand the universe's evolution from the Big Bang to today. It incorporates dark energy, lambda, and cold dark matter, CDM. For decades, lambda CDM has been incredibly successful at explaining many cosmological observations. But now the James Webb Space Telescope is throwing a wrench into the works. The model predicts certain things about the early universe: how quickly galaxies should form, their size distribution, and their overall structure. Webb is peering back into that early universe, and what it's seeing, well, it doesn't quite match the predictions. Specifically, Webb is finding evidence of massive, fully formed galaxies existing far earlier than lambda CDM allows. These aren't small, proto-galaxies slowly coalescing. We're talking about behemoths, galaxies with mature stellar populations, appearing within the first few 100 million years after the Big Bang. According to lambda CDM, there simply wasn't enough time for these galaxies to form so quickly. The model dictates a slower, more gradual process of structure formation. Gravity needed time to pull matter together, for stars to ignite, and for galaxies to assemble themselves piece by piece. Yet Webb is showing us that the universe was already teeming with large, well-developed galaxies at a cosmic dawn that should have been relatively quiet. The problem isn't just the existence of these early galaxies, it's their abundance. The simulations based on lambda CDM predict that such galaxies should be exceedingly rare in the early universe. Webb is finding them everywhere it looks. It's like going to a desert and finding it filled with lush rainforests. Scientists discovered this discrepancy early in 2023 as the first datasets trickled in. It caused quite a stir, to say the least. Some initially dismissed it as a calibration error or some other instrumental artifact. Maybe Webb was seeing things that weren't really there. But as more data poured in, the evidence solidified. These early massive galaxies are real. The implications extend beyond just tweaking the parameters of lambda CDM. If the model is fundamentally wrong about the speed of galaxy formation, then it could also be wrong about other things, like the nature of dark matter or the properties of dark energy. Consider the possibility that dark matter isn't as cold as we thought. Cold dark matter refers to particles that move slowly, allowing them to clump together more easily and seed the formation of galaxies. If dark matter is warmer, meaning the particles move faster, it would suppress the formation of small-scale structures in the early universe. However, it wouldn't necessarily prevent the formation of large, massive galaxies. A warmer dark matter model could potentially explain Webb's observations, but it would also require a significant rethinking of our understanding of dark matter's fundamental properties. Or maybe the problem lies with our understanding of dark energy. Dark energy is the mysterious force that's causing the universe to expand at an accelerating rate. Its properties are poorly understood, and it's possible that it behaved differently in the early universe. A different form of dark energy could have altered the expansion rate of the universe in a way that allowed galaxies to form more quickly. But again, this would require a significant departure from the standard lambda CDM model. It's not just about tweaking parameters. We're talking about potentially needing to rewrite entire sections of the cosmological textbook. Here's what's wild. Some scientists are even questioning the validity of the cosmological principle itself. The cosmological principle is the assumption that the universe is homogeneous and isotropic on large scales, meaning it looks roughly the same in all directions and at all locations. This assumption underlies much of our cosmological modeling. If it turns out to be incorrect, then our entire picture of the universe could be skewed. The analysis continued, revealing that perhaps the early universe wasn't as uniform as we thought. Maybe there were regions of higher density where galaxies could form more easily, or maybe there were variations in the fundamental constants of nature that affected galaxy formation. These are radical ideas, and they're not being proposed lightly, but the data from Webb is so compelling that scientists are forced to consider all possibilities, no matter how outlandish they may seem. This means that our current understanding of the universe, built upon decades of research and observation, may be incomplete or even fundamentally flawed. It's a humbling realization, but it's also an exciting one. It means that there are still profound mysteries waiting to be uncovered, and that the next generation of telescopes and experiments may revolutionize our understanding of the cosmos. And then there's the question of whether we're even asking the right questions. Webb just revealed something massive about how galaxies actually formed in the early universe. We always thought we had a pretty good handle on this, a nice, neat picture of how things came together. But the new data is throwing that picture into serious doubt. The standard model of galaxy formation goes something like this. After the Big Bang, the universe was filled with a nearly uniform soup of matter and energy. Over time, gravity caused slight density fluctuations in this soup to grow. Regions with slightly more matter than average attracted even more matter, eventually collapsing to form galaxies. These early galaxies then merged and collided to form the larger galaxies we see today. That's the textbook version anyway. But Webb is showing us galaxies that are far too massive and far too mature to have formed so quickly after the Big Bang. These aren't just slightly bigger or more evolved than expected. They're dramatically different, challenging the entire timeline of galaxy formation. Consider this. If you see a 5-year-old who's 7 feet tall and has a full beard, you're going to question your understanding of human development, right? It's the same thing here. These galaxies are cosmic toddlers with the physiques of seasoned bodybuilders. The problem isn't just their size, it's also their composition. These early galaxies are surprisingly rich in heavy elements, like carbon, oxygen, and iron. These elements are forged in the hearts of stars and then scattered throughout the universe when those stars die. The presence of so many heavy elements in these early galaxies suggests that star formation was much more rapid and efficient than we previously thought. So, how did these behemoth galaxies form so quickly? That's the million-dollar question, and right now, nobody has a definitive answer. One possibility is that the early universe was simply more efficient at forming stars than we realized. Maybe the conditions were just right for gas clouds to collapse and ignite into stars at a much faster rate. This could be due to factors like higher gas densities, stronger gravitational forces, or even differences in the way dark matter interacted with ordinary matter. Another possibility is that our understanding of how galaxies merge and grow is incomplete. Maybe galaxies in the early universe were able to merge much more rapidly than we thought, allowing them to quickly accumulate mass. This could involve processes like cold accretion, where galaxies directly siphon gas from the intergalactic medium, bypassing the slower process of merging with other galaxies. There's also the possibility that we're missing some fundamental physics. Maybe there are new particles or forces at play that influenced galaxy formation in the early universe. Some scientists have even suggested that the laws of gravity might have been slightly different in the past, allowing structures to form more quickly. These are all just hypotheses at this point, of course. But the fact that we're even considering such radical ideas shows just how profoundly Webb is challenging our understanding of the universe. It's not just about tweaking our models or refining our simulations. We're talking about potentially needing to rewrite the entire story of galaxy formation. And this isn't some minor detail that can be swept under the rug. Galaxy formation is a fundamental process that underpins our understanding of the entire cosmos. If we don't understand how galaxies formed, then we can't understand how the universe evolved to its present state. The implications extend far beyond just astrophysics. Understanding galaxy formation is crucial for understanding the distribution of matter in the universe, the formation of stars and planets, and even the emergence of life. If our current understanding of galaxy formation is wrong, then it could have profound consequences for our understanding of everything else. Further examination revealed that the problem might not just be with individual galaxies, but also with the large-scale structure of the universe itself. Our current models predict that galaxies should be distributed in a certain way, with a network of filaments and voids that reflects the underlying distribution of dark matter. But Webb is showing us that the distribution of galaxies in the early universe might be very different from what we expected. For example, some observations suggest that galaxies in the early universe were more clustered together than our models predict. This could indicate that the density fluctuations in the early universe were larger than we thought, or that the way dark matter interacts with ordinary matter is more complex than we currently understand. This means that our entire picture of the cosmic web, the large-scale structure that shapes the distribution of galaxies, might be wrong. And if that's the case, then we need to rethink our entire understanding of how the universe evolved from its earliest moments to its present state. And then there's the unsettling possibility that our assumptions about the fundamental nature of dark matter are wrong. Dark matter makes up about 85% of the matter in the universe, and it plays a crucial role in galaxy formation. But we still don't know exactly what dark matter is. Our current models assume that dark matter is made up of weakly interacting massive particles, or WIMPs. But WIMPs have never been directly detected, and some scientists are starting to question whether they even exist. If dark matter isn't made up of WIMPs, then it could have very different properties that affect galaxy formation. For example, some alternative dark matter models propose that dark matter is made up of axions, sterile neutrinos, or even primordial black holes. Each of these models would have different implications for how galaxies form and evolve. And if our assumptions about dark matter are wrong, then we need to completely rewrite our models of galaxy formation. The implications extend to the very formation of supermassive black holes. We're talking about black holes with masses millions or even billions of times that of our Sun, sitting at the centers of most galaxies. And the puzzle has always been, how did they get so big, so fast? The conventional wisdom says these behemoths grew over billions of years, gradually accreting matter from their surroundings. But Webb is finding evidence of supermassive black holes existing much earlier in the universe than we thought possible, within the first billion years after the Big Bang. How could they possibly have grown so massive in such a short amount of time? One possibility is that they started out as much larger seed black holes than we previously imagined. Instead of forming from the collapse of individual stars, these seed black holes might have formed directly from the collapse of massive gas clouds in the early universe. These direct collapse black holes could have been tens of thousands, or even hundreds of thousands, of times the mass of our Sun right from the start, giving them a huge head start in the race to become supermassive. The problem is, the conditions required for direct collapse black hole formation are very specific and rare. You need a pristine environment with very little heavy elements, because heavy elements can cool the gas and cause it to fragment into stars instead of collapsing into a black hole. You also need a strong source of radiation to suppress star formation in the surrounding area. Webb is helping us find these pristine environments in the early universe, and it's also revealing the presence of strong radiation sources. That could have triggered direct collapse, but even if direct collapse black holes did exist, it's still not clear how they could have grown so quickly to become the supermassive black holes we see today. Another possibility is that black holes in the early universe grew much more efficiently than we thought. Maybe they were able to accrete matter at a rate much closer to the theoretical maximum, known as the Eddington limit, than we observe in black holes today. Or maybe they were able to merge with other black holes more frequently, growing in leaps and bounds instead of gradually accreting matter. The data reveals that galaxies in the early universe were much smaller and more chaotic than galaxies today, with frequent mergers and interactions. These mergers could have funneled large amounts of gas and dust into the central regions of galaxies, feeding the black holes and causing them to grow rapidly. Furthermore, the discovery of overmassive black holes in small galaxies raises a serious question. According to conventional theory, the size of a galaxy's central black hole is tightly linked to the size and properties of the galaxy itself. Bigger galaxies tend to have bigger black holes, and smaller galaxies tend to have smaller ones. But Webb is finding examples of small galaxies with surprisingly large black holes, which challenges this relationship. It's like finding a chihuahua with the teeth of a great white shark. It just doesn't fit the expected pattern. This suggests that the black hole-galaxy connection might not have been as tight in the early universe as it is today. Perhaps black holes were able to grow independently of their host galaxies, or perhaps the galaxies themselves evolved in a different way than we thought. Consider this. Maybe the very early universe was simply a different beast altogether. The rules we observe today might not have fully applied back then. It's possible that the density of matter was so high and the conditions so extreme that black holes could simply gobble up material at rates that are impossible in the present-day universe. Or perhaps some exotic new physics was at play, something we haven't even conceived of yet. Here's what's wild. Webb's observations are forcing us to confront the possibility that our entire understanding of black hole formation and growth is incomplete. We might be missing a crucial piece of the puzzle, some fundamental aspect of the early universe that we haven't yet grasped. And then there's the unsettling implication that the seeds of these supermassive black holes might have played a more active role in shaping the evolution of galaxies than we previously thought. Instead of just passively sitting at the center of galaxies, these black holes might have actively influenced the formation of stars, the distribution of gas, and the overall structure of their host galaxies. If that's the case, then we need to rethink our entire picture of galaxy formation. We need to incorporate the effects of these early black holes into our models and simulations, and we need to understand how they interacted with their surroundings to shape the galaxies we see today. This means, well, it means a lot more work. But it's exciting work, driven by real observation. You've been lied to about galaxy formation, the neat, orderly picture we often see, a slowly swirling disk of stars gradually coalescing over billions of years. Webb is suggesting something far messier, far more chaotic, and frankly, a bit terrifying. It's not just about tweaking the existing models, it's about potentially scrapping them and starting over. The early universe, as revealed by Webb, appears to have been a period of rampant, almost ungoverned growth, where black holes and galaxies were locked in a chaotic dance, influencing each other in ways we're only beginning to understand. This isn't just a minor correction to our understanding. This is a fundamental shift in perspective. We're talking about rewriting textbooks, redoing simulations, and rethinking the entire history of the cosmos. The implications extend beyond just black hole formation and galaxy evolution. If these early black holes were indeed so influential, then they likely played a crucial role in seeding the universe with the heavy elements necessary for life. The very atoms that make up our bodies, the Earth, and everything we see around us might owe their existence to the violent activity of these ancient behemoths. Think about it. A black hole, typically considered a destructive force, might have been instrumental in creating the building blocks of life. The universe is full of irony, isn't it? And then there's the question of dark matter. We still don't know what dark matter is, but we know it makes up the vast majority of the universe's mass. Could these early black holes somehow be related to dark matter? Could they have played a role in its distribution? It's a speculative idea, but Webb's observations are opening up new avenues of investigation that were previously unthinkable. Scientists discovered something else that's really making them scratch their heads. The James Webb Space Telescope is so powerful that it can peer through the dust clouds that obscure many distant galaxies. And what it's finding is, well, it's unexpected. It's finding galaxies that are far more mature than they should be at such early epochs. Galaxies that appear to have well-defined spiral arms, central bulges, and all the hallmarks of a fully formed galaxy, existing just a few 100 million years after the Big Bang. That shouldn't be possible. Our current models of galaxy formation predict that galaxies should take billions of years to reach that level of maturity. Yet, Webb is showing us galaxies that are already there, seemingly defying the laws of physics. This is forcing astronomers to reconsider their assumptions about how quickly galaxies can form. Perhaps there are mechanisms at play that we haven't yet accounted for, some sort of accelerated galaxy formation process that allows galaxies to rapidly assemble in the early universe. Or perhaps again, our timeline is off. Perhaps the universe is older than we think, or perhaps the early universe was simply a much more efficient galaxy-building machine than we ever imagined. Meanwhile, there's a nagging concern that our understanding of redshift, the phenomenon that allows us to measure the distance to faraway objects, might be incomplete. Redshift is based on the idea that the universe is expanding uniformly, stretching the wavelengths of light as it travels across vast distances. But what if that expansion isn't as uniform as we thought? What if there are local variations in the expansion rate that are skewing our distance measurements? If that's the case, then the distances to these early galaxies might be wrong and they might not be as far away or as early in the universe's history as we currently believe. This would still be a major problem, as it would call into question our entire understanding of cosmology, but it would at least alleviate the need for these impossibly rapid galaxy formation scenarios. The analysis continued, and here's another unsettling thought. What if our fundamental constants of nature aren't as constant as we assume? We take it for granted that the laws of physics are the same everywhere in the universe and at all times. But what if that's not true? What if the speed of light, the gravitational constant, or other fundamental constants were slightly different in the early universe? Such variations could have profound effects on the formation of galaxies and black holes, potentially explaining some of the anomalies that Webb is observing. It's a radical idea, but it's one that scientists are seriously considering. This means the universe we thought we knew, the universe neatly described by our equations and simulations, is starting to look a lot less predictable, a lot less orderly, and a lot more alien. It's a universe where the rules are still being written, where the unexpected is the norm, and where our current understanding is just a tiny piece of a much larger, far more complex puzzle. And the truth is that's both terrifying and exhilarating. Terrifying because it means we have so much more to learn, that our current knowledge is so limited. But exhilarating because it opens up new possibilities, new avenues of discovery, and a chance to finally unravel some of the universe's deepest mysteries. But it's not just the really distant galaxies that are causing a stir. Are we fundamentally wrong about gravity? It's a question that's starting to be whispered in cosmology departments around the world. Webb's observations of these early galaxies and their black holes simply don't fit the standard model. And when your observations clash so spectacularly with your theory, you have to start considering that maybe, just maybe, the theory itself needs a serious overhaul. The current model of gravity, Einstein's theory of general relativity, has been incredibly successful at explaining the behavior of the universe on large scales. It predicts the expansion of the universe, the existence of black holes, and the bending of light around massive objects, all of which have been confirmed by observations. But general relativity is not without its problems. It doesn't play well with quantum mechanics, the theory that governs the behavior of matter at the subatomic level, and it requires the existence of dark matter and dark energy, two mysterious entities that make up about 95% of the universe but whose nature remains completely unknown. Could it be that general relativity is an incomplete description of gravity? Could it be that it works well enough on the scales we've been able to observe until now, but that it breaks down in the extreme conditions of the early universe, or in the vicinity of supermassive black holes? Some physicists are exploring alternative theories of gravity that might be able to explain the Webb observations without invoking exotic physics, like impossible galaxy formation or variable fundamental constants. These theories often involve modifications to general relativity, such as adding extra dimensions, introducing new fields, or changing the way gravity interacts with matter. One promising avenue of research is modified Newtonian dynamics, or MOND. MOND proposes that at very low accelerations, gravity behaves differently than predicted by Newton's law or general relativity. This could explain the observed rotation curves of galaxies without the need for dark matter, and it might also have implications for the formation of early galaxies and black holes. Another idea is that dark matter is not made up of weakly interacting massive particles, or WIMPs as is commonly assumed, but of some other more exotic type of particle. Perhaps dark matter interacts with itself or with ordinary matter in ways that we don't yet understand. Such interactions could affect the formation of galaxies and black holes, potentially resolving some of the tensions between theory and observation. And then there's the possibility that dark energy is not a constant, as is assumed in the standard cosmological model, but that it varies with time or space. This could have profound effects on the expansion rate of the universe and on the formation of large-scale structures like galaxies and galaxy clusters. These are just a few of the ideas that scientists are exploring in an attempt to reconcile the Webb observations with our current understanding of the universe. It's a challenging task, but it's also an incredibly exciting one. It could lead to a revolution in our understanding of gravity, dark matter, dark energy, and the origin and evolution of the universe. Let's examine the implications. If our understanding of gravity is fundamentally wrong, then everything we thought we knew about the universe could be called into question. Our models of galaxy formation, black hole growth, and the expansion of the universe would all need to be revised. Our estimates of the age and size of the universe could be off. Our understanding of the fundamental laws of physics could be incomplete. It's a sobering thought, but it's also a necessary one. Science is a process of constant questioning and refinement. We should never be afraid to challenge our assumptions and to consider alternative explanations, no matter how radical they may seem. That's how we make progress. That's how we learn. That's how we unravel the mysteries of the universe. Scientists discovered that Webb's data also forces us to re-evaluate our understanding of stellar evolution. The early universe was a very different place than it is today. The first stars were likely much more massive and hotter than the stars we see around us now. They lived fast and died young, exploding as supernovae and seeding the universe with heavy elements. But how did these first stars form? What were their properties? And how did they affect the evolution of the galaxies in which they lived? Webb is providing us with unprecedented insights into these questions. It's allowing us to observe the light from the first stars and galaxies, giving us a glimpse into the conditions that existed in the early universe. And what we're seeing is challenging our current models of stellar evolution. The stars in these early galaxies seem to be forming and evolving in ways that we don't fully understand. They seem to be more massive and more metal-poor than we would expect. And they seem to be forming at a much faster rate than we thought possible. This could be due to a number of factors. It could be that the conditions in the early universe were simply different than they are today. The gas clouds from which these stars formed may have been denser, hotter, and more turbulent. Or it could be that our understanding of stellar physics is incomplete. We may be missing some key ingredients in our models of star formation and evolution. Whatever the reason, it's clear that Webb is forcing us to rethink our understanding of stellar evolution. It's showing us that the early universe was a much more dynamic and complex place than we ever imagined. And it's giving us new clues about the origin and evolution of the stars and galaxies that we see around us today. The implications extend beyond just stellar evolution. It also affects our understanding of the chemical evolution of the universe. The first stars were responsible for creating all of the heavy elements in the universe, the elements that make up our planet and our bodies. When these stars exploded as supernova, they scattered these elements into the surrounding space, seeding the next generation of stars and galaxies. But how did this process happen? How were the heavy elements distributed throughout the universe, and how did they affect the formation of planets and life? Webb is helping us to answer these questions by allowing us to observe the chemical composition of early galaxies. It's showing us that the heavy elements were not as evenly distributed as we thought. Some galaxies seem to be much richer in heavy elements than others, and some regions within galaxies seem to be more enriched than others. This could have profound implications for the formation of planets and life. Planets need heavy elements to form, and life as we know it requires a certain amount of carbon, oxygen, and other elements. If the heavy elements were not evenly distributed throughout the universe, then some regions may have been more conducive to the formation of planets and life than others. So, the question remains, are we fundamentally wrong about gravity? Or stellar evolution? Or the chemical evolution of the universe? Or all of the above? It's impossible to say for sure at this point, but what is clear is that Webb is challenging our current understanding of the universe in profound ways. It's forcing us to rethink our assumptions and to consider alternative explanations. And it's opening up new avenues of discovery that could lead to a revolution in our understanding of the cosmos. And then there's the black hole situation. 600 galaxies, all seemingly too massive, too early. That's the impossible number Webb is throwing in our faces. It's not just a few outliers, it's a whole population of galaxies that shouldn't exist, according to our current understanding of cosmology. And then there's the black hole situations. We're finding supermassive black holes at the centers of these early galaxies, ones that are far too big for their age. How did they grow so rapidly in the early universe? Our models simply can't explain it. It's like finding a fully grown adult in a kindergarten class. It just doesn't add up. Consider this. These black holes are ravenously consuming matter, emitting tremendous amounts of energy. This energy can heat up the surrounding gas, preventing it from collapsing and forming new stars. This process, known as black hole feedback, is thought to regulate the growth of galaxies. But if these black holes are already so massive in the early universe, then their feedback effects would have been even more pronounced. They would have stunted the growth of their host galaxies, preventing them from becoming as large as they are today. So we're left with a paradox. The galaxies are too big, and the black holes are too big, and the two problems seem to contradict each other. It's a cosmic puzzle that's challenging everything we thought we knew about galaxy formation. The analysis continued. Scientists discovered that many of these early galaxies are also incredibly bright, shining with the light of billions of stars. This suggests that they're forming stars at a furious rate, much faster than galaxies today. But here's the rub. Star formation requires cold, dense gas. And in the early universe, the gas was much hotter and more diffuse. So how were these galaxies able to form so many stars so quickly? It's another mystery that Webb is forcing us to confront. Measurements show that these early galaxies are also surprisingly well organized, with spiral arms and other structures that we typically associate with more mature galaxies. This is unexpected because the early universe was a much more chaotic place, with galaxies colliding and merging frequently. So how did these galaxies manage to form such orderly structures in such a turbulent environment? Did they somehow avoid the worst of the collisions? Or did they have some other mechanism for organizing themselves? We simply don't know. The implications extend to our understanding of dark matter. Dark matter is a mysterious substance that makes up about 85% of the matter in the universe. It doesn't interact with light, so we can't see it directly. But we know it's there because of its gravitational effects on galaxies and other structures. According to our current models, dark matter played a crucial role in the formation of galaxies. It provided the gravitational scaffolding that allowed gas to collapse and form stars. But if the early galaxies are too massive, too bright, and too well organized, then this suggests that our understanding of dark matter may be incomplete. Could there be some other form of dark matter that we're not aware of? Or could dark matter interact with itself or with ordinary matter in ways that we don't understand? These are questions that Webb is helping us to explore. And then there's the question of reionization. In the early universe, the gas was neutral, meaning that the hydrogen atoms were not ionized. But at some point, the universe underwent a process called reionization, in which the hydrogen atoms were stripped of their electrons. This process is thought to have been driven by the first stars and galaxies, which emitted copious amounts of ultraviolet radiation. But the exact details of reionization are still a mystery. How did the ultraviolet radiation escape from the galaxies, and how did it spread throughout the universe? Webb is helping us to answer these questions by allowing us to observe the ultraviolet light from the earliest galaxies. It's showing us that the ultraviolet light was not as evenly distributed as we thought. Some regions of the universe seem to have been reionized earlier than others. And some galaxies seem to have been more effective at reionizing their surroundings than others. This could have profound implications for the formation of galaxies and the evolution of the universe. Reionization could have affected the way that gas cooled and collapsed, influencing the formation of stars and the growth of galaxies. Here's what's wild. All these anomalies are interconnected. The overly massive galaxies, the oversized black holes, the rapid star formation, the well-organized structures, the dark matter mysteries, the reionization puzzles. They're all pieces of the same cosmic jigsaw puzzle. And Webb is giving us the pieces, but we still don't know how to put them together. Are we missing some fundamental ingredient in our models? Are we overlooking some crucial physical process? Or are we simply asking the wrong questions? It's a humbling experience to realize how much we still don't know about the universe. But it's also an exciting one. Webb is opening up new vistas of discovery, challenging our assumptions, and forcing us to rethink our place in the cosmos. This means every simulation needs rewriting. Every textbook needs updating. Every cosmologist needs to be hitting the books again. It's a fantastic time to be alive and witnessing this revolution in our understanding. Meanwhile, the data keeps pouring in. Each new image, each new spectrum, each new measurement is adding to the mystery. And as we delve deeper into the unknown, we're likely to encounter even more surprises. The universe is a vast and complex place, full of wonders and enigmas, and Webb is our window into that universe, allowing us to explore its deepest secrets. The unfolding mystery is far from over. It's only just begun. What if the key lies not in modifying existing models, but in questioning the very foundations upon which they're built? How did we get this so wrong for so long? It's a question that haunts anyone working at the edge of knowledge. The universe, as revealed by Webb, isn't just bigger than we thought. It's different, fundamentally. Our models, painstakingly built over decades, are showing cracks, not subtle hairline fractures, but gaping chasms that threaten to swallow the whole edifice. We've relied on certain assumptions about the early universe, how quickly galaxies formed, how star formation proceeded, how dark matter behaved. Webb is telling us those assumptions are, at best, incomplete. At worst, they're flat out wrong. Consider the implications. We thought we understood the basic timeline of the universe: the Big Bang, inflation, the cosmic microwave background, the Dark Ages, Ryanization, the formation of the first stars and galaxies. But Webb is showing us that galaxies were already mature, massive and complex much earlier than our models predict. This throws the entire timeline into question. What processes were at work in the early universe that allowed these galaxies to form so quickly? It's not just about tweaking the numbers in our simulations, it's about confronting the possibility that we're missing something fundamental. Maybe our understanding of gravity needs revision. Maybe dark matter isn't what we think it is. Maybe there are physical processes at work that we haven't even imagined yet. This can be unsettling, even terrifying. To dedicate your life to understanding something, only to discover that your understanding is flawed. That's a tough pill to swallow. But it's also what makes science so exciting. It's a constant process of questioning, revising, and refining our knowledge. And Webb is giving us the tools to do just that. The temptation, of course, is to cling to our existing models, to try to force the new data into our old frameworks, but that would be a mistake. We need to be open to the possibility that our current understanding is fundamentally incomplete. We need to be willing to question our assumptions, to challenge our preconceptions, and to embrace the unknown. Think about it this way. For centuries, people believed that the Earth was the center of the universe. It took a revolution in thinking, a willingness to challenge established dogma to arrive at a more accurate understanding of our place in the cosmos. We may be on the cusp of a similar revolution now. The universe is under no obligation to conform to our expectations. It is what it is, and it's up to us to figure it out. Webb is giving us a glimpse of the universe as it truly is, in all its complexity and mystery. It's a daunting task, but it's also an incredibly exciting one. Further examination revealed that the light from these early galaxies is also more redshifted than expected. Redshift is a measure of how much the light from an object has been stretched by the expansion of the universe. The higher the redshift, the farther away the object is, and the earlier in the universe's history it existed. The fact that these early galaxies are so highly redshifted suggests that they are even more distant and more ancient than we previously thought. This poses another challenge to our models of galaxy formation. How did these galaxies manage to form so quickly and become so massive so early in the universe's history? What physical processes were at work that allowed them to buck the trends predicted by our simulations? The implications extend beyond just galaxy formation. The early universe was a very different place than it is today. It was hotter, denser, and more chaotic. The conditions were ripe for the formation of exotic particles and physical processes that we don't see in the universe today. Webb is giving us a window into that early universe, allowing us to study these exotic conditions firsthand. This could lead to breakthroughs in our understanding of fundamental physics, helping us to unravel the mysteries of dark matter, dark energy, and the origin of the universe itself. Scientists discovered that even the distribution of elements in these early galaxies is surprising. We expect the first galaxies to be relatively pristine, composed mostly of hydrogen and helium. But Webb is showing us that some of these galaxies are already enriched with heavier elements, like carbon, oxygen, and iron. This suggests that these galaxies have already undergone multiple generations of star formation and supernova explosions. How did this happen so quickly? Where did these heavy elements come from? The data reveals a universe far more dynamic and complex than we ever imagined. It's a universe that is constantly surprising us, challenging our assumptions, and pushing the boundaries of our knowledge. And then there's the unsettling possibility that some of the anomalies we're seeing are not just due to our incomplete understanding of physics, but also to our limited ability to observe the universe. We're seeing these galaxies as they were billions of years ago, and the light from them has been traveling through vast stretches of space and time. Could some of the anomalies we're seeing be due to intervening gas clouds, gravitational lensing, or other effects that we haven't fully accounted for? It's a humbling reminder that we're still in the early stages of exploring the universe. We've only just begun to scratch the surface of its mysteries. But with Webb, we have a powerful new tool that will help us to delve deeper into the unknown and to unlock the secrets of the cosmos. If you found this exploration of the cosmos fascinating, be sure to subscribe for more deep dives into the mysteries of our universe.